So before starting, let us look at what some of the concepts that we needed this week. So um, we're looking at eigenvalues, basically eigenvalues, vectors, and uh, diagonalizability, etc. Um, Let us start off with the first problem then. I hope you can see my screen. So, well, the first problem is for this given matrix, what is the algebraic and geometric multiplicities of each of the eigenvalues? So, what do you just to recall, what do you mean by the geometric uh, and algebraic multiplicities of an eigenvalue? So, recall that the characteristic equation of a uh, linear operator. Uh, so let's say A is my linear operator. Let's say I call FA the characteristic equation of my linear operator. So this FA is a polynomial in A, which is equal to determinant of A minus lambda I. Sorry, I said it's a polynomial in lambda, not a polynomial in A, of course. Now if you can write this, if you can write this polynomial in lambda as some product of lambda minus. Actually, let's not use the symbol lambda. Let's just call it x minus a minus xi. So if you can write this as equal to product of x minus uh, lambda I for I to the power of ri, then so essentially you've decomposed this this polynomial into a product of these irreducible polynomials, these irreducible terms raised to the powers ri. Uh, then these lambda i's are the eigenvalues. And the power that you see is the multiplicity of that eigenvalue. So we'll call Ri as the algebraic multiplicity of um, lambda I. And so now, of course, for us, if lambda I is an eigenvalue, then that means that the linear map A minus lambda I times I. This, of course, then of course the null space of this operator of this map. So the null space of this map is basically equal to the eigenspace. This is definition. This is equal to the eigenspace of lambda I. So essentially, it's the space of all the eigenvectors corresponding to lambda I. So that means that AV is equal to lambda times V, where V is a V is an eigenvector corresponding to lambda. Now the rank of this, or not the rank, but the nullity of this operator, or equivalently the dimension of this eigenspace. So the dimension of V such that AV is equal to lambda I times V. This is the definition of what we call the geometric multiplicity of lambda I. Now, we'll look at diagonalizability, but we can briefly, I'll just briefly state it somewhere else. So in order that a particular matrix is diagonalizable, you need the algebraic and the geometric multiplicities of each of the eigenvalues to be the same. Okay. So we'll talk about that later. So first, let's look at this particular problem. Um, you're given this matrix, and you have to basically solve for the eigenvalues of A. So it's given that the eigenvalues of A are 4 and 1 respectively. So in order to, now there are of course multiple ways uh, to to find the eigenvalues of A, of the matrix A. You can try to change this matrix into some kind of an into some kind of an upper triangular form maybe. But in this case, it is easiest to just solve the characteristic equation. So we're going to solve for determinant of A minus lambda I. No, not A minus lambda I, determinant of A minus xi to be equal to 0. And this gives us 2 minus x minus 1, 1, minus 1, 1, 2 minus x minus 1 minus 1, 2 minus x to be equal to 0. Okay, now kind of skipping the computation where you can do the computation, and there isn't anything fancy going on. It's just doing the computation, um, and you get this to be equal to x minus 1 squared times x minus 4. So of course you know the algebraic multiplicity of 1. Of 1 is 2, and that of 4 is 1. Okay. Now, of course, we have to check if this is equal to the geometric multiplicity of this matrix. Now, of course, the full-fledged way to show this would be to actually um, uh, take this matrix, which is A minus uh, A minus lambda I. So not lambda. I mean here lambda is equal to 1 and 4. So consider A minus lambda I, and of course try to compute the rank of this matrix. So compute the rank of this guy A minus lambda I. Now um, now the geometric multiplicity of this matrix of this eigenvalue lambda will be equal to the nullity of this matrix. So once you know the rank, you know the nullity. The nullity would just be equal to the dimension minus the rank. Okay. So let me just write it here. So then the nullity of A minus lambda I would be equal to the n minus the rank of A minus lambda I. Okay. Now, of course, you know how to compute rank of matrices. We have done this in the previous exercises where we have tried to where given a matrix we have tried to reduce the matrix to a row echelon form, and then once you have it in one of these echelon forms, you can try to read off the number of zero columns. Either it could be some column uh, it could be a column form or a row form. Just read the number of zero rows or zero columns, however you have reduced it, and that would give you the nullity of the matrix. Okay, so the nullity would be equal to the geometric multiplicity of the eigenvalue. Now, but you can do that without necessarily doing this whole exercise by making this observation that A is a symmetric matrix. So let us just pause here for a moment. So A is a real symmetric matrix. And let us make a few comments about these. Okay. So a real symmetric matrix always has real eigenvalues. So essentially we have A transpose is equal to A. Just give me one moment. Sorry, I'll just be back in 1 minute. Yeah, sorry. Um, so this always has real eigenvalues. The second is that this is an additional point. The uh, the eigenspaces always are always mutually orthogonal, which means that if lambda I and lambda j are two distinct eigenvalues, and if and if v let's say and if vi and vj are two eigenvectors corresponding to lambda I and lambda j, then they are going to be mutually orthogonal, which means that vi times vj, this is the inner product, is equal to 0, or uh, write them in standard coordinates, then vi transpose vj is equal to 0. Okay, this is the second point. And the third point to remember is that A is diagonalizable, which is just equivalent to saying, let me just quote it over here, that for each eigenvalue, lambda is an eigenvalue, the algebraic multiplicity of lambda is equal to this geometric multiplicity of lambda. Okay. And so A is diagonalizable. You can write this A as equal to P inverse dp, okay, where these matrices P can be, so this is basically a vector. This is uh, uh, so this transformation matrix, this P, can indeed be an can be an orthogonal matrix. Okay, so P can be, so we can always choose an orthogonal basis um, of eigenvector. So let me just write it down. So which means that we can choose, this follows from this point, we can choose an orthonormal basis of eigenvectors. Okay. Now, of course, corresponding to that basis, whatever that orthonormal basis is, so let's say P is this orthonormal basis, then the matrix, then the linear map with respect to this basis would be just would just be a diagonal matrix where the entries are each of the eigenvalues, and because uh, P is an orthogonal matrix, so this is basically means that P is a orthogonal matrix. Therefore, P transpose P is equal to In. So we can indeed choose this P to be an orthogonal matrix where we can write this A to be equal to P transpose dP. Okay. So these are some of the facts. And if we use these facts, then because this is a symmetric matrix, so the algebraic multiplicities and the geometric multiplicities would be the same. Okay. So I hope this is clear. All right, so let's move on. Okay. Um, okay, trying to look up some good problem. So just bear with me for a moment. Okay, let's. So let me give you a problem. Not finding too many sort of uh, problems which are tricky. So let me give you a problem, and you can think about this problem for a little bit, and then I can give you the solution. Okay. Maybe you've thought about this problem. So um, let's just work it out. Um, yeah, I mean, there is nothing very fancy about this. So let's say A, C, D, B, and 1, comma 1 is an eigenvector. So this is equal to some lambda times 1, comma 1, or lambda is the eigenvalue. So which gives us basically A plus C. Uh, okay, okay. Um, okay, so if 1, comma 1 is an eigenvector of AC, comma DB, and uh, if I consider this matrix, then this matrix will have a determinant of okay. Let's try to see this. Have A minus lambda, B minus lambda, C D. Okay. Okay. So so I can write this as equal to a plus c comma d plus b, right? But let's call this a plus c equal to some k. So then this is equal to some k times 1 comma 1. Okay. So one of the eigenvalues is a plus c, is an eigenvalue. Now, whatever the other eigenvalue is, we would have a plus c plus whatever this other eigenvalue lambda, that is equal to a plus b. So this other eigenvalue must be equal to b minus c. Yeah, okay. So let's move on. Right. So this is an example of a matrix where the geometric multiplicity and the algebraic multiplicity not going to be the same. Okay. So if you take consider this matrix A, then the characteristic equation reads like lambda minus 2 cube is equal to 0. So this eigenvalue 2 has an algebraic multiplicity of 3. But if you want to compute the geometric multiplicity, so if we consider this matrix A minus 2 times I, then this is equal to 0, 0, 0, 4, 6, 0, 0, 0, 0. Okay. So it is obvious, I mean, it's already in a canonical form. So it's obvious that the rank of this matrix is equal to 1 and the nullity of this matrix is equal to 2. So the nullity of A minus 2i3 is equal to 2. So the geometric multiplicity is 2, whereas the algebraic multiplicity is 3. Okay. So this is an example why, and this is how you can actually determine if the matrix is diagonalizable or not. Uh, if the multiplicities don't match, then that implies that the matrix is not diagonalizable. Even though the matrix has has all real eigenvalues. So having all real eigenvalues, it therefore turns out to be not a sufficient condition for a matrix to be diagonalizable. It is a necessary condition, of course, but it is not a sufficient condition. The sufficient condition comes from from these multiplicities. The multiplicities must match. Okay, so I hope this was clear. Let's look at another problem. Let's look at this one. Right. So again, you have this matrix A, and you have this. Uh, this matrix is in upper triangular form. So of course, if the matrix is in upper triangular form, you can just read the eigenvalues very easily. The eigenvalues are just going to be the entries on the diagonal. Now of course, from here we have to state whether it is diagonalizable or not diagonalizable. Uh, so can you, so can someone give like a quick argument whether A is going to be diagonalizable or not? We can see that the eigenvalues are 5, 3, minus 5. Is A going to be diagonalizable? Any idea? I'll let you think for like a minute and then I'll answer. Okay, so yes, A is going to be diagonalizable. And why is A going to be diagonalizable? Because so of course, in order to check diagonalizability, as I said, we need to have all real eigenvalues. So we do have all real eigenvalues, but we also need to check for the multiplicities of those eigenvalues. Now you see that um, uh, the algebraic multiplicities of each of these eigenvalues is 1, of course. The geometric multiplicities would also have to be equal to 1, right? Because each eigenvalue, because the eigenspace of each eigenvalue is at least of dimension 1, you have 3 different eigenvalues. So we can conclude that the dimension of the eigenspace of each of these eigenvalues is exactly equal to 1. It is at least equal to 1, and in this case, it is also exactly equal to 1. So the algebraic and the geometric multiplicities are the same, and therefore A is diagonalizable. Okay, so if A is diagonalizable, I can write this A as equal to some P inverse dP. And what is A squared? A squared is equal to P inverse dP times P inverse dP. So this is equal to P inverse d squared P. So if D is a diagonal matrix, then of course D squared is also a diagonal matrix. And so both A and A square are going to be diagonalizable. In fact, you can just probably see over here, check quick that A power K is equal to P inverse D power K P. So all powers of A are going to be diagonalizable. Uh, what more can we say? Well, not just all powers of A are going to be diagonalizable. Let's just make a quick few observations. All powers of A are diagonalizable. And the second observation is that all polynomials in A, it just follows from this, all polynomials in A are also diagonalizable. So these are two facts that will hold for any diagonalizable matrix. Okay. Why is this true? I can you can very clearly see this. Why? So if you have any polynomial of the form some ck ak plus ck minus 1 ak minus 1 up to some c0, if this is a polynomial in A, then of course this is equal to, by this formula, this is just equal to P inverse, and then you have this entire expression, which is ck dk all the way to c naught times P, which is just equal to P inverse of this polynomial evaluated on this diagonal matrix times P. Okay. So a polynomial evaluated on a diagonal matrix is always a diagonal matrix. PD is also diagonal. Okay. Hope this is clear. Let's on. Okay, let me find a problem. Still looking up. Okay, just give me 1 minute. I'm trying to look up a problem. Just bear with me for like 2 minutes. Okay, let me just bring up this problem. I'll let you think for like a minute or two. Then I'll give the solution. Okay. Let's see. Okay. Okay, let's try to solve this problem first, and then we'll come to this particular problem. Okay. And I'm not sure how to figure out the solution of this. Let's look at this problem first. Um, so we're looking at this problem. So A is a real symmetric matrix, and B is equal to I plus uh, this essentially this complex matrix. Now, uh, what can we say about B and A? So notice that we'll use the properties of real symmetric matrices here. So if A is a real symmetric matrix, it is necessarily diagonalizable. So we can write this A to be equal to P inverse D times P. Okay. So then B, which is equal to I plus uh, root over minus 1 times A, can be written as, so I write this I as P inverse times P plus P inverse times dP, of course, multiplied by square root of minus 1. So this gives us this matrix, which is P inverse I plus square root of minus 1 times D times P. Okay. Now, of course, the question is, um, what can we say uh, about the first? Let's look at the first option, which is B is invertible if and only if A is invertible. So clearly, if A is invertible, then B is also invertible. And the reason why it's invertible because um, because if you look at the entries of this diagonal matrix, then all the entries of this diagonal matrix are non-zero. So these are, of course, a complex matrix, and the entries in the diagonal are all non-zero. Okay. So which means that in particular, I plus square root of minus 1 times D is invertible. But the only if I mean uh, the sufficiency part is uh, is correct, but A need not be invertible. So in particular, D need not be invertible. Because D need not be invertible, but B is always going to be invertible because this matrix is invertible. So this is the correct option. Um, what can I say about the other options? What about B minus I? B minus I is equal to I times A, but this I times A need not be uh, invertible. It can very well be non-invertible. Um, all the eigenvalues of B are necessarily real. Again, that's obviously uh, not true unless D is a zero matrix. And D is a zero matrix basically means that unless A is zero. So unless A is zero, all the eigenvalues of B are not real. Um, yeah, so C is the correct option. Right. So if A is a 5 cross 5 matrix and the dimension of the solution space of X is at least 2, then what can we say about the rank of A squared? So here it is given that the null space of A, the so the null space of A has a dimension greater than or equal to 2. Now, so if you denote this null space by NA, then we can always find a complementary subspace, right? So if NA is the null space, I can always find a complementary subspace, which I call W over here, um, such that this is equal to, let's say, R power 5. But this complex on this so on this complementary subspace, the map A, so basically A restricted to W is an injective map. And if NA has dimension greater than or equal to 2, then this um, then this W has a dimension which is less than or equal to 3. And this dimension of W is basically the rank of A. Okay. So rank of A is less than or equal to 3. If rank of A is less than or equal to 3, that means that the rank of A squared should also be less than or equal to 3. So C is the correct option. Okay. Okay, just give me 1 minute. Okay, so let's look at this problem. Right. So T is an n cross n matrix with this particular property, and I'll let you think about this question, and then I'll answer. Okay. So, so here we're going to make the additional assumption that, uh, I mean, the problem doesn't say this, but we have to make the assumption that t to the power n minus 1 is not equal to 0. Okay. So if t to the power n minus 1 or some lower power were to be equal to 0, then we cannot necessarily make one of the statements that we're going to make here. So assume that t to the power n is equal to 0. Okay. Now, of course, if t to the power n is equal to 0, then of course you notice that the that this is the characteristic polynomial of this particular matrix T, and um, the eigenvalues of this matrix are all equal to 0. And so this 0 eigenvalue occurs with a multiplicity of n, right? Um, so indeed, T has one eigenvalue of multiplicity n, which is this 0 uh, eigenvalue. But T has n distinct eigenvalues. That's obviously not true because the characteristic polynomial of T is actually T to the power n equal to 0. So it does not have n distinct eigenvalues. Uh, 0 is definitely an eigenvalue of T, and T is similar to a diagonal matrix. This statement is also false. And well, okay. Why is this statement false? Well, this t to the power n is equal to 0. Uh, I mean, this is going to be a diagonal matrix if and only if this n is equal to 1, which means that t is identically equal to 0. So it's diagonalizable. Okay. So these kinds of matrices are called nilpotent matrices. Um, yes. So uh, right. And why do you need this t to be equal to 0 if and only if it is well we discussed before that the algebraic and the geometric multiplicity should be same for the matrix to be diagonalizable. Now the algebraic multiplicity of 0 is exactly equal to n. But if the geometric multiplicity of n were to be also equal to n, then you require that the matrix is 0 everywhere. So essentially, it means that um, which means that essentially t of x, the dimension of x such that t of x is equal to 0 is equal to n. This means that um, this this means that the geometric multiplicity of 0 is n, but this is just equivalent to saying that t is identically equal to 0. Okay, which is how we get this condition. Um, so yeah, so t is definitely not similar to a diagonal matrix unless n is equal to 1. Um, so this is the correct option. Okay, so I hope this was clear. Okay. Yeah, I mean, there are plenty of things in linear algebra. Um, I don't think everything is necessarily there in the syllabus. I would have ideally liked to talk about a few more things. Um, but as I said, it's not necessarily there in the syllabus. Okay. Okay. So I think I don't have anything more to discuss. If you have any questions, you can ask me. I'll be here for another 10 minutes. Yeah, I don't have any more questions to discuss. I think everything else that I'm seeing are fairly computational questions. I think I've more or less discussed uh, all the questions which need a certain concept. Uh, so yeah, remember this algebraic and geometric multiplicity thing. Um, they need to match for the matrix to be diagonalizable. Um, yeah. Yeah. Also, symmetric matrices always have um, symmetric matrices always are diagonalizable. Okay, I think we'll stop here today. I don't think there are any more questions. So let's stop here today. So from next week, I think we're going to start some vector calculus. So we're going to see some new things from next week. Okay. So